Applications of forces, dynamics and connected particles. Example 1. So we have a mass of 5 kilograms which is connected by a light inextensible string over a smooth pulley to another mass of 10 kilograms. The incline is rough, so frictional forces have to be considered. So these are all of the forces in play. So for this block we have its weight, we have friction, which is opposing motion because the block will move up the incline, the normal reaction and the tension in the string. And for this block we have its weight and the tension in the string. The 5 kilogram mass has a 5g weight, the 10 kilogram mass has a 10g weight. The block is accelerating up the incline. The frictional force will have reached its maximum value. F equals mu r gives us, from this value here for mu, 0.2 r. That's our frictional force acting down the incline, opposing motion. The acceleration of this block will be equal to the acceleration of this block. We're given that tan alpha is equal to 3/4, so we need to work out sine alpha and cos alpha using basic trigonometry. We look at the forces on this block separately from this one. So let's start with this. Block P. So resolving forces perpendicular to the incline, taking this as the positive direction. In this direction there's no acceleration, the resultant force is 0. Everything is in equilibrium. So R minus, and the force in this direction will be 5g cos alpha, and that's equal to 0. And we know what cos alpha is. It's 4/5, like so. And then we can work out the value of R. It's equal to 4g newtons. Now resolving forces parallel to the incline and taking this as the positive direction because we have motion in this direction. So we have F equals ma and the resultant force, so T, and this arrow is in this direction, that's positive, and 5g sine alpha will be the component of this force in this direction. So minus 5g sine alpha minus 0.2 r is equal to the mass times the acceleration, and we know that r is equal to 4g. We know that sine alpha is 3/5. So T is equal to 3.8g plus 5a. We have an equation here that we need to work on further. Now looking at the mass Q, which is hanging on this string, taking this as the positive direction because it's accelerating downwards, and this was from the previous calculation that we just did. So F equals ma, and we have to use Newton's second law because we have acceleration. So 10g downwards, positive, minus t is equal to the mass times the acceleration. So then we have 10g minus, now t was 3.8g plus 5a. That's the tension in the string, and the tension in the string here and on the other side is exactly the same. So there's the tension equals the mass times the acceleration. So we simplify, and then we can work out the acceleration. In terms of g, that's the exact value, or we can say 4.05 meters per second squared. And we can substitute this value back in here to work out the tension in the string, like so. It's 57.5 newtons. So looking at the pulley and the string on each side, the tension is 57.5 newtons. This angle is 53.1 degrees. Angles in a right angle add up to 180. We want the magnitude of the force caused by the string on the pulley, and that force is represented by K on this diagram. And there's a right angle triangle here. Here we go. And K is equal to 57.5 cos 26.6 degrees. And there's a contribution from the tension from this part of the string and from this part of the string. And the contribution from each side is exactly the same. So if we're looking at forces in this direction, in the direction of our force K, so 57.5 cos 26.6, which is this, but we've got to multiply it by 2 because there's two strings which are equally contributing. So K is 103 newtons. For further practice, try these questions.